Chapter 2, Video 2. Today we're going to talk about the action potential, and I'm going to be quite honest with you guys. I want you to know the basics of the action potential. However, I don't want you to get yourselves so stumped up on it because it can get really in depth and it can be cumbersome. So just know the basics of what I tell you here. With the action potential, we have different phases. We have phase, I'm not sure why phase 4. We're going to start with phase 4, but then we have phase 0, phase 1, and phase 2, and phase 3. So at phase 4, the cardiac cell is at rest, okay? This is the negatively charged with a resting transmembrane of negative 90 millivolts. This is the flat line. This indicates electrical silence, okay? So this cell is actually at rest during phase 4. Phase 0, the cardiac cell is then stimulated. Depolarization occurs. The sodium rushes in and the potassium leaks out. This corresponds with the QRS complex on the EKG, okay? So we see that spiked waveform that represents depolarization of the ventricular myocardium. The cells charge above the 0 mark, and the cell is then positively charged, okay? So this is when depolarization actually happens in phase 0. Phase 1 and 2, we have early repolarization. Calcium, this is important, guys, because we've been talking about sodium and potassium. But during phase 1 and 2 with repolarization, calcium is released, resulting in ventricular contraction. And remember, I said calcium has a direct effect on the ventricular contraction and the ventricle function. When we think about phase 1 and 2, this corresponds with the ST segment on the EKG that we're going to go over. So the flat line on the EKG that follows that QRS complex. And then with phase 2, this is called the Plateau Phase. And this is where those waveforms level off. So, and we'll go over what the EKG strip looks like shortly. But there in phase 3, we have rapid repolarization. The sodium and potassium return to their normal places via the sodium potassium pump. So the sodium and potassium are returning to normal, meaning the sodium's going back outside, the potassium's coming back inside. This corresponds with the T wave on the EKG, which is a broad rounded wave that follows the ST segment, and it represents ventricular repolarization. So as we scroll over, I want you to know the phases and what it represents, what's happening, basically what's on the slide, but I don't want you to worry about getting so involved in this that you get yourself stumped up. With the action potential, this is a clip of the EKG strip. So when you look at this, you can kind of see, you can refer to this slide when you're looking at the phases of the action potential and where it happens. With refractory periods, refractory basically means resistant to, okay? So with absolute, there's no stimulus can cause depolarization. Absolutely cannot accept another impulse because it's dealing with the last one, okay? So an example of this would be the way I like to refer to this, it's busy, okay? It can't take in anything else. It can't accept another impulse because it's still dealing with the last one that it received. So it's kind of like flushing your toilet. You flush your toilet, but can you turn around and immediately flush your toilet again and it flushed twice? No. You have to wait till that cycle is finished before it can accept another one. And then we have the relative. It's a strong stimulus that can cause depolarization. Back to that example, the toilet will flush, but it's not the same rigor. It's still kind of weak because it hasn't fully refilled and fully recovered. And then we have the supernormal period. Even a weak stimulus can cause depolarization. The cardiac cell during the supernormal period is considered hyper. Stimulation at this time can result in a very fast and dangerous rhythm. So with the supernormal period, this can be dangerous. And then we have our refractory periods here. This shows you where they're happening at. So we have a P, Q, R, S, T. This is what a strip, this black line right here, represents a normal EKG strip, which we're going to get into more detail with later. But for right now, you can see where this is happening on that strip. That strip will make sense to you once we go over exactly what you're looking at there. And that's going to be on our next lecture. If you have any questions, please let me know.